Okay, in the last class, we have studied temperature measurement, various techniques, and how we can measure the temperature. We can do the calibration and those things. And today we are going to study the destructive test. That means in the metallurgy, to obtain the mechanical properties of the material, we need to do the destructive some tests to obtain the mechanical properties. For example, it can be like tensile strength, compressive strength, bending strength, and as well as strain modulus, rigidity, hardness, toughness. Okay, all these properties you need to know, and to know them, we need to do the destructive tests. And there is also some non-destructive test technique to obtain different kind of properties. But today we are going to focus on only the destructive tests. Uh, First is the hardness. Hardness is the technological property of the material, and there can be various hardness tests, and depending on the it can be categorized into three different categories. First one is the elastic hardness, which works within the range of the elasticity of the material. And the second one is the resistance to cutting or abrasion. This one acts like how resistant a material is in terms of cutting or in terms of abrasion, that means erosion. And the third one is resistance to indentation. If you want to indent something, that means if you want to apply force with using a indenter or harder material into the softer material, how does it behave? These three categories are for measuring hardness. The first one, in the elastic hardness, is measured with the help of scleroscope. The scleroscope actually measures the energy absorption of the material, how much elastic energy has been absorbed by the material, uh, and it is basically the measure of the resilience of the material. And the resilience is the mechanical property of the material which within the elastic limit. Okay, if the material is within the elastic limit, then if, for example, if I want to show you uh, a stress versus strain curve, to just to make sure you understand the resilience. Does anyone know what is resilience? Anyone? Nobody? Okay. Uh, then let's say this is sigma axis and this is strain, and we got a stress strain curve like this. Okay. And in this curve, if we see that up to this point, this is the elastic limit. This point is the elastic limit of the material, and the area under this curve is called uh, the resilience of the material. That means elastic energy absorbed by the material within the elastic limit. Okay, or it can be like stress strain, or it can be like force versus displacement. If it is force versus displacement or stress versus strain, whatever it is, okay, you'll get the same value, like now the energy under the elastic curve. Okay, and in the case of scleroscope, what happens is that a small diamond tip indenter, which is shown here, uh, expanded view of the indenter. This is the indenter here, and this indenter we raise it to a certain level. Let's say for at position 1, and this is the workpiece in which we want to do the hardness test. That means the elastic hardness test. That's the indenter is raised up to that position. That means a height of h1. Okay, then that indenter will have a potential energy of if the indenter mass is m, and G is the gravitational constant, and H1 will be the height of the indenter with the hammer. Okay, and once you release that indenter from the top position, once you release it, it drops on the surface of the specimen, and then it springs back. Okay, and how we need to measure the how much the spring back occurs. Okay, uh, and that height is like h2. After the striking on the specimen surface, the indenter has a spring back effect because of the elasticity of the material, and it comes back up to height h2. Then the potential energy at this point is mg h2. Then how much energy is absorbed by the specimen? Can anybody say?
MgH1 minus MgH2.
Mgh2. It's exactly, or in the short form we can write like mg in the bracket h1 minus h2. Now this is the elastic energy absorbed by the specimen. Okay, and that is the measure of the elastic hardness of the material. Okay, and this hardness, this amount of energy absorbed by the material will be different based on the properties of the material. For example, if you want to use a specimen as wood as a specimen, okay, if you use wood as a specimen, then the amount of elastic energy absorbed will be much higher compared to if you use a protiles, okay, or if you use a metallic specimen. Then if the indenter will go back very high, will spring back very higher. That means h2 will be very close to h1 if you use a metallic specimen. Okay, and that's how we compare the hardness. That means less the energy absorbed, higher the uh, hardness of the material. Did you understand that? Do you have any question?
Yes, sir.
স্যার ওই ওয়ার্ক পিসটা উপরে স্যার ডায়মন্ড টিপ হ্যামার ওটা কি স্যার আমরা উপর থেকে ছেড়ে দিছিলাম নাকি স্যার ওটা মেকানিক্যালি ওটা আসতেছে স্যার?
Yes, we have released it. We raise it to a height of h1
ফ্রি
and then release it freely. Okay, just drops down. Did you get it?
স্যার ইয়েস স্যার।
Okay, any other question? No. Then we move to the next one. This one is called resistance to cutting or abrasion. It means if you want to cut a metallic wire with a, for example, hacksaw, and if you want to cut a, for example, wooden or bamboo or anything else, something like that, then which one would be the easier for cutting, wood or is it going to be wood or metal or plastic? If you want to compare the cutting of plastic and metal, the easier would be like if you use wood, if you compare between like wood and metal, then wood will be much easier. So wood has less hardness compared to metal. Okay, that's how the cutting resistance to cutting hardness measure is works. And another one is abrasion. This one is also the cutting is also kind of abrasion, removal of the material. Okay, it's kind of same. And it can be differentiated into two different types. One is scratch test, uh, and another one is file test. I'll go to the file test later. First, we'll discuss the scratch test. In the case of scratch test, that means you make scratches on the surface of the material. Okay, and that's how we test the resistance to cutting or resistance to scratch. Okay, and for to do the scratching, what should we use for to do the scratching? And in that case, we have like 10 standard minerals which are numbered 1 to 10 here. Okay, talc, gypsum, calcite, fluorite, apatite. Okay, these are the 10 different material we use to make the abrasion or scratching on the surface of the material which we want to do the conduct the hardness test. Okay. For example, you have a you have mild steel, you have a mild steel specimen, okay, and you use quartz, okay, quartz quartz particles, silicon dioxide particles, which have an absolute hardness of 100, okay, and use the silicon dioxide particle to create the scratch on the surface, okay, and then you use uh, the corundum, okay, aluminum oxide, corundum in another same specimen, another specimen. For example, if it is mild steel, let's say it is a stainless steel, okay. So sorry, I was moving to another direction. Anyway, the first you start scratching with silicon dioxide, and you see both of the specimen is mild steel, okay, both of the specimen is mild steel. You start scratching with quartz silicon dioxide, and you see after some time you see there is no scratch on the surface of the material. That means silicon dioxide could not uh, abrade the surface material. That means could not remove the surface material from the mild steel, okay. And but when you use topaz, then you see a little bit of scratching occurs on the surface of the material. First you use silicon dioxide and you see there is no scratch. Then you use topaz, then you see there is a little bit scratch on the surface. That means the hardness of mild steel will lie between 100 to 200, okay. So the hardness of the mild steel will be between 100 to 200. In the similar way, if you have an unknown material, then how do you start testing? Okay, you start with the talc. Start with the talc for some time. You scratch on the surface using talc, and there is no abrasion on the surface. There is no scratch on the surface. Then you stop scratching with the talc. Then you go to gypsum. If gypsum cannot produce any scratches on the surface, then go to calcite. Once you find it, for example, when you use the fluoride, then you got the scratch on the surface. Then the hardness of this material will be between 2 to 9. Okay, so that's how we do the scratch test for the comparison of hardness. Okay, is using 10
স্যার
different.
স্ক্র্যাচ টেস্টের জন্য
Okay, I
স্যার
couldn't.
স্ক্র্যাচ টেস্টের জন্য স্যার ওই যে প্রেসার ফোর্সটা কি আলাদা হবে নাকি ওটা কি
No, no,
কনস্ট্যান্ট হবে?
everything has to be constant. How long you will scratch with the talc, and how much vibration or how much force will be exerted, blasting would be given. It has to be constant. Otherwise, you can't compare. Okay, you can only change the material and check whether it is scratching or not. Okay, did you understand?
জি স্যার, জি স্যার।
Okay, any other question here?
No, sir.
Okay, then we move to the next one, that is file test. How do you do the file test? For file test in the heat treatment industries or metal industries or like steel industries, there is a term called heat treat until the material is file hard. Okay, and the meaning of this is that you have a file, that means the file that you have used in the machine shop. Do you remember?
Yes, sir.
Yes, you use the file to make the hexagon shape of the bolt, right?
Yes, sir.
Okay, so that file has a certain known hardness, okay, and that file can create a scratch on a surface of a material which have hardness less than that file. For example, if you have a file of hardness 100 and you want to uh, scratch a material of hardness 60, then it is possible, right? But if the hardness of the material is 160, then using the file of hardness 100, you cannot create any scratch on the surface of this material. Okay, that's how this test work. It depends on the capacity. The file has the capacity of 100, so it cannot go over that. Okay, and how does it work with the heat treatment? With using the heat treatment, actually what happens is that steel, softer steel can be made very harder, and sometimes can be made very steel with hardness, let's say 65, can be if you do the hardening, then you can make it harder, like 94. The hardness can be 94 or 95. Okay, then you have a file of let's say you need the hardness of the material has to be greater than 90. Okay, the hardness of the material has to be greater than 90. Then how do you do the quality control test? Then you need to have a file of hardness 90. Okay, then you do the heat treatment on the steel which have hardness 65, and then the heat treat until uh, after the heat treatment, a cycle of heat treatment, you do the scratching with this file and see there is a scratch. That means the hardness has not increased more than 90. Okay, and then you do the heat treatment again. Once you see that the file with 90 hardness cannot create any scratch on the surface of the material, then you are sure that the hardness of the heat treatment has been done. Okay, that's how you do the quality control test, and that's how the file test work. Any confusion?
স্যার হিট ট্রিটমেন্টের সময় তো মানে ম্যাটেরিয়ালটা অনেক মানে গরম থাকে আর মানে একটু সফট হয় আর কি, তখন কি এটা স্ক্র্যাচটা করা ঠিক হবে নাকি?
No. You need to do the sampling. It's not done like always. Okay, it is done for experimental purpose. You got a different batch of material. Okay, you are going to produce a a lot of product out of that. Then you need to do the heat treatment. Okay, in that case you do the initially and then you do the periodically. Did you understand?
তার মানে মানে কিছু হিট ট্রিটমেন্ট করব, তারপরে ওটা ঠান্ডা হয়ে যাওয়ার পরে তারপরে টেস্ট করব,
Yes, of course.
এরকম ভাবে নাকি?
Yes, of course. After heat treatment of certain number of samples, you take some samples and do the hardness test. Okay, if it fails, then you have to think that let's say you do the heat treatment for 20 minutes. Okay, and then you take out the sample and you cool it to the room temperature, and then you do the hardness test. If it fails, then you have to increase the time, heat treatment time, because sometimes the heat treatment depends on the time, depends on the temperature, it depends on the cooling medium. There are a lot of other variables. You will be we will discuss about them, about the heat treatment in the later section. But in this case, your question was that whether we should do it in the soft state. Of course not. After solidification and at room temperature, then you do the heat treatment, then you do the test. Okay.
স্যার হিট ট্রিটমেন্ট করলে হার্ডনেসটা বাড়বে নাকি মাত্রা?
Not always. Using heat treatment, you can make softer. Using heat treatment, you can make it harder. Okay, both can be done. Depends on the process, how you do it. Okay, we'll discuss in detail heat treatment. There is a chapter. Okay.
জি স্যার।
All right. Next one is the resistance to indentation. In the case of resistance to indentation, there are 4 methods for hardness test: Renal, Rockwell, Beakers, and micro hardness test. Okay, we'll cover all of them. For Renal hardness test, okay, for Renal hardness test, a steel ball hardened steel ball. That steel ball was hardened and is used as indenter and forced into the specimen. Okay, and the standard ball diameter is 10 millimeter, and the force that you exert on the ball is like 300 kg for ferrous and 500 kg for non-ferrous materials. And how long you want to indent? It's the 10 seconds for ferrous and 30 seconds for non-ferrous metals. And the indentation diameter, after indenting, the diameter of the indentation has to be measured with the help of microscopic ocular scale. Okay. This is the case. What happens is that you have a ball of 10 millimeter diameter, you apply a load 500 kg for non-ferrous, 3000 kg for ferrous material. Once the indentation is complete, there will be a impression on the surface. Okay, there will be an impression on the surface. You remove the ball and load everything, and then you measure the diameter of the impression, how much how indentation has occurred. Okay, then if you know the diameter, then you can know the depth. Okay, and you don't need to measure the depth. So if you know the diameter of the indented surface, then you can calculate the Renal hardness number. And as I already said, like hardness is the measure of, it's a kind of comparison. Okay, if larger the penetration, if the penetration is higher, the hardness will be less. Penetration is smaller, the hardness number will be higher. Okay, and the thing is to compare, like the Renal hardness number, you need to strictly maintain the load, diameter of the indenter, and the time, and the time required, time you allow to indent on the surface. If you change any of these parameter, if you change the load, you keep the time and ball diameter same, but if you have changed the load, then you cannot compare with other material. Then the indentation diameter will be different, and in that case you will get a different hardness number. Okay, and then using the formula here, like Renal hardness number HB, it is usually designated as HB, and this is the load you are using, and the diameter of the ball, and small d is the diameter of the indentation, and you get the Renal hardness number. There are tables available. Since the diameter is constant, load is constant, the only thing that is changing is the diameter of the impression on the surface. Okay, and since the diameter of the impression is changing, then there will be a lot of tables available based on the indentation diameter. If the indentation diameter is 1 millimeter, then hardness will be that indentation diameter. It's kind of a graph. It doesn't have to be a table. It can be graph, like HB in the vertical axis, and then small d is in the horizontal axis. Then it can be a graph. Okay, with the change of diameter, the hardness number will also decrease, actually, not increase. Okay. And in the case of Renal hardness test, it has a limit of 500 HB, because the hardened steel ball that you are using itself has a hardness of 500 HB. So you have a capacity to eat like 2 biryanis, then you cannot have 3 biryanis, right? So in that case, the limitation of this Renal hardness test is that hardened steel ball has a hardness of 500 HB, so you cannot measure beyond that. And if you want to increase, there are means to increase the Renal test range. That if you want to increase it, like up to, it can be done up to like 650 HB by using tungsten carbide ball, because the tungsten carbide ball has higher hardness than 650 HB. That means the main thing is that if you want to test the higher hardness, you need to have the testing ball needs to be harder than the material. Okay, if the material has 1000 HB, then you need to do conduct the test using a ball of hardness more than 1000 HB. That's the main thing. Do you have any question here? All right. And how do you represent the hardness number? For example, a material after testing of Renal hardness, you got a hardness number of 75, and if you want to say, if you just say that the hardness number is 75 of this material the hardness number is 75, it doesn't actually mean anything, because there are so many hardness tests. Okay, there is Renal, Rockwell, uh, Beakers, micro hardness. There are a lot of hardness tests. Then which one you need to indicate using HB? Okay, you need to have the HB hardness number. That means HB indicates it is Renal hardness number. And what about this? The first number 10, what is it? Can anybody say?
Diameter of the ball.
বল
No. This is the diameter. Sorry. This is the diameter of the indenting ball. That means capital D. This is a constant, right? For all the cases, either ferrous or non-ferrous, the
Yes.
diameter of the ball is constant. And the next one, 500, what is it?
It's a load.
pressure.
That's the load. Is it for ferrous material or non-ferrous material?
It's non-ferrous.
Okay. And the time? 30 is
30 seconds.
30 second. For non-ferrous material, you know that we have to use 30 second. So this is the specification. Once you are told that what is the hardness number, if you are told that test the hardness of this material, then you do the testing, you get the number, and you specify the number using this, so that anyone can compare with this material. Okay, anyone can compare your data. Like, for example, someone said like for this same material, you are saying like the hardness is 75. Someone said the hardness is 65. You should not say that he is wrong unless you know his testing parameters, whether he did the test, Brinell hardness test, whether he used 10 millimeter diameter ball, whether he or she used like 500 kg load or 3000 kg load, and then how long did he expose it. Okay, once you know everything, then you can say, okay, this is comparable. Okay, any question?
No, sir.
All right. So the next one is Rockwell hardness test. The principle is based on differential depth measurement. I think you have already done mathematics, right? 2 mathematics, math 1, math 2. Did you complete all of them?
Yes, sir.
Okay. So can anybody say what is differential depth, or what does it mean by differential depth? When we use the differential term, the term differential, let's say we have a length this, okay, this is the x, and the length has increased by delta x, right? Then we say differential increase of length. Okay, so we use the method of principle of differential depth measurement in the case of Rockwell hardness test. That means we do a indentation, certain indentation, like for example up to this we do the indentation, and then we use another force to do another indentation, and then we measure the differential change of depth, and that depth actually gives us the Rockwell hardness number. And to explain better, the initially fixed minor load is applied on the specimen, which is 10 kg for normal tester and 3 kg for superficial tester. The superficial tester is used for measuring the hardness of thin specimens. Okay, don't be confused with that. The normal tester, the thickness is higher, but for sheet metals or some like those thinner materials, we use the superficial tester. For the case of superficial tester, the minor load is 3 kg, but for the normal tester, if you have a block of material, then you use 10 kg load as a minor load. Once you use the minor load, that minor load actually is here, that's preload applied. Okay, once you apply a preload, then you get a certain amount of indentation here. Can you see this? A certain amount of indentation in here on the surface of the material. Then you
Yes, sir.
apply the measured load, which is 60, which can be 60, 100, 150 for normal, and for superficial it can be 15, 30, 45, depends on the scale which you are using, because the Rockwell hardness testing has different scales, A, B, C, E, F, G, there are a lot of scales. Okay, and for based on the scales, you change the loads like 60, 100, 150 kg, whichever it is. If you use scale B, then you will have all these values, like how much force you need to apply. So when the major load is applied, when the minor load is applied, you get the deflection, the indentation this much, and then when the main load is applied, then you get further indentation like this much. Okay, you get further indentation of this much, and then after some time you release all these loads. Then what happens is that there is an elastic recovery. Okay, that means a certain amount of recovery will occur. That means this much is the elastic recovery. And what would be the final depth? Differential depth will be this much. This much will be the differential depth of indentation. That means that will be the permanent depth of indentation. Okay, and once you get the permanent depth of indentation, then you can measure the Rockwell hardness number. Okay, like for example, you have a minor load indentation is like H1, and then major load indentation is like H2. Okay, then you can measure the hardness number like this using different scales. There are so many scales actually, Rockwell scale, which have the value of scale changes based on the indenter, like barrel, diamond indenter. Then major load will be 60, 1/16 inch ball in the scale B. Then the major load will be 100. Okay, and the minor load is fixed like 10 kg, and the major load will be changing based on the scale, and then you calculate the hardness number using this formula. And that's what I said in here, like for different scales, and there are some different hard steel balls of diameter, and also we use like 120-degree conical diamond. Okay, Samira bolo.
স্যার আমাদের কি এখানে কোনো টাইমিং প্যারামিটার আছে, নাকি আমাদের লোডটা একবার জাস্ট 1 সেকেন্ডের জন্য যাবে বা এরকম কিছু?
There is timing parameter. A certain amount of time has to be applied. I don't have the exact value here, but there is time. Okay, otherwise the permanent deformation will be changed. Okay, depending
sir.
on the time.
Yes, sir.
Okay. So any other question here?
So indentation গুলো যদি আরেকবার একটু বলতেন স্যার, H1 H2, তারপর স্যার ওই ইলাস্টিক রিকভারি ওই জিনিসটা স্যার।
The elastic recovery is not very important actually. It's very negligible. I think that's why some people actually don't consider that. Okay, as you see in the first one here they have considered the elastic recovery and then calculated the permanent depth of indentation. Okay, I think this is the proper way to analyze it, because you need to have the after recovery you measure the depth. Okay, but in this case it could be a little bit different, like after elastic recovery, or since it is measuring the differential depth. Okay, first you create a certain amount of depth and then you create the uh, yeah, you apply the major load, and then you measure the differential length. That means on the next image what we see here is that the H1 is the uh, depth of indentation because of the minor load applied before, and then you use the major load, then you get the H2, then the difference between H1 and H2. Yep, that is it. I think that's right. Once you create a deformation of H1 on the surface, and then this one is H2 is the overall from surface to the final depth. Okay, and then you you subtract H2 by H1. Okay, then you get the differential depth of indentation, and that differential depth of indentation gives you the hardness number. Okay, did you understand it?
Yes, sir.
Okay.
Yes, sir.
The elastic recovery is considered in here. Okay, for the minor load the elastic recovery is very small. Okay, and for the major load there would be a bit of elastic recovery. Okay, and that one is also considered in here. Okay, once you remove the major load, then the elastic recovery is already considered in here. Okay, okay, any other question here? No. And how do you represent the number, hardness number? In the case of Rockwell hardness test, you use 75 is the Rockwell hardness number, HR indicates the Rockwell hardness, and B indicates the scale B in here. Okay, and what does the scale B means? The scale B means that you are using 1 over 16 inch steel hardened ball with a major load of 100 kg. The major load can also be like 100 kg with a different diameter steel ball, and then the scale will be changed. It will be like E. Okay, so you need to be really careful which scale you are testing and which scale you are told to do the hardness test. You have to be really careful on that. And also for the formula, if you are using like m equals to 100 for A, C, D scales, and for other scales m equals to 130. Okay, okay, the next one is Beakers hardness test. In the case of Beakers hardness test, a square base diamond pyramid indenter is used, which have a included angle of 136 degree. Actually, a square based diamond pyramid indenter means that when you do the impression on a surface, it will create a square surface. It will create an indentation which will have like square edges. Okay, something like that. And the load range that is used in here is 1 to 120 kg, and the basic principle is same as the Renal hardness tester. Okay, you use the same method as the Renal hardness testing, and the impression in the surface is square. That's what I said. And what do you measure? You measure the diagonal length. Okay, the length, you measure the diagonal length of the impression, like D1. Okay, or D2, then you can average out between D1 and D2. You just need only one. Okay, and can be used to measure the hardness of thin sheets. This can also be used to measure the hardness of thin sheets. And how does it work? For, let's say you have three different samples, sample A, sample B, sample C, of different material. then you use the same load, you use the same time, and you measure the diagonal length of the impression. Since it has a smaller impression, it will be harder than the larger impression of sample C. So the hardness, Beakers hardness of sample A will be higher compared to the Beakers hardness of sample C. Okay, and the formula, we have the formula here for diamond indenter. The formula is like Beakers hardness is V is equals to 1.854. L is the load that you are using, and D is the diagonal length. Okay. So any question?
Sir, why do we do this test? I mean, what is the uniqueness?
Of the Beakers hardness test?
Yes, sir. I mean, do we get any special features here?
Yes, yes, of course. We have different application for this actually. The Beakers hardness test is mostly used for thin materials. Okay, because it has a very sharp corner with a 136-degree angle, sharp cone. Okay, and that is why you can create very tiny impression on the very small thickness material. But using the ball, it is very difficult. Okay, that is why the Beakers hardness
Yes.
test. I'll go to them actually. There is a slide which contains like which test, which hardness test is suitable for which material or which application. Okay. Okay. Any more
Okay,
questions?
sir.
No. So the next one is the micro hardness test. This one is also for kind of Beakers hardness test, but also used with very small load. If you have like if you want to do like a hardness test on the crystals of a material, you have a material here which you see under when you see under the microscope, you see there are some grains, right? In the metallography, we have studied that. If you want to do the
Yes, sir.
hardness test on a grain, on a crystal, like for example here, then you can use this micro hardness tester. Okay, it uses very small amount of load, and you need to have like microscopes to see the impression. Okay, and two, for the ease of measurement, in this one is the indenter that we have previously seen for the Beakers hardness test is like 136 degrees square Beakers diamond pyramid, was like the impression was like a square, but this one is not a square. Okay, it is elongated in one side. Okay, so once it is elongated, then actually this indenter is called noob indenter, noob diamond indenter, and this noob diamond indenter, because of using this noob diamond indenter, this test is also called noob hardness test. Okay, this test is also called noob hardness test. And why do we use this elongated area? Because of the ease of measurement. Okay, the measurement is much easier. Okay, and the other side, if you know this side, then other side can be known very easily using the structure of this, because of the dimension of this noob indenter. Okay, and the hardness number is the load per unit area of impression. How much impression area has been created is the uh, hardness number for micro hardness test, and that is 14.229 load divided by diameter, the elongated diameter. The long diameter will be used in here. Okay, any question?
No,
Okay,
sir.
actually, do you have, if you have any question, please ask. Okay, we have plenty of time. All right, then we'll move to the next. That's all about the hardness test, and I have a very important slide in here. It says the factors affecting the hardness test. There are so many factors that can affect the result of your hardness test. The first one is the condition of the indenter. if the indenter is rusty, then can you get the actual result?
No, sir.
No. If the indenter is broken,
No, sir.
and I have a practical example for this, like condition of indenter. Uh, in our mechanics lab, we have been testing the hardness of steel pipes, and after testing, actually the Minamonir does the testing. After doing the testing, he gave me the sample and I was measuring the diameter. I see there is no sharp round. Okay, the indenter should produce a very measurable the diameter of impression. Okay, if not, then you have to check the ball whether the ball is okay. I have seen that the indenter, it was supposed to be perfectly round, and I saw that it is like this way and that way, like this. Okay, then I was confused, like what happened. Then when I saw the ball, it was broken. Okay, and there was nothing on one side of the ball, and that is why the indentation is not complete. If the indentation is not complete, the result will be very misleading. Okay, so you need to be really careful about the condition of the indenter, accuracy of the load applied, the load that you are applying, it has to be accurate. If it says 300 kg, it has to be 300 kg. And another important thing is impact loading. Do you load suddenly or do you load slowly? Okay, and in the case of hardness test, you have to apply the loading slowly. Okay, otherwise if you do the impact loading, the indentation diameter will change. Okay, if the indentation diameter is changed, then the hardness value will also change. And that is why if you do the apply the loading slowly, then it will be uniform for all the cases. So impact loading should be avoided. Okay, do you understand impact?
Yes,
Anyone?
sir.
Do you understand impact? What is impact loading?
Yes, sir.
Okay, only you understand or everyone understand?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay, so what we need to do is like we have to avoid impact loading. And the fourth one is the surface condition. If the surface is rough, surface is rusty, okay, then you will not get the exact result. That is why you need to do the proper conditioning of the surface. The surface has to be really plain and smooth. Using the emery paper or file, you need to prepare the surface for testing the hardness. And the thickness has significant effect. Okay, you when you do the impact testing, you put the let's say this is a specimen. Okay, and you put it on the surface, a very hard surface. Okay, and you do the using the ball, you apply the load, you do the hardness test, and if the thickness is larger, then it will not be affected. But if the thickness is smaller, then the diameter of impression will be affected by the support. Okay, and that is why you need to really carefully choose which test method you should use for hardness test, whether you should go for Beakers test or micro hardness test, or you can do the Renal. Okay, then thickness is one of the important parameter. And the shape of the specimen, if the specimen shape is not perfectly flat, then you cannot do the testing, because if you on a flat surface of the specimen, you will say it will be perfect. Okay, but if the bottom surface of the specimen is okay, but top surface is slightly inclined, and you do the indentation using the ball, then what will be the indentation? It will be like this, like, right? So
Non-uniform, sir.
non-uniform. So it will actually when you measure the indentation, then you will measure this, right? You'll measure this, but
Sir.
actually indentation occurred on this way, so it will be misleading and the result will not be valid. You need to really careful about the shape of the specimen. It has to be flat on the flat surface. And the location of the impression, at least 2.5 to 5 diameters from edge. Where do you do the test? You do the indentation. Sometimes what happens is that people think like I have a space uh, like 10 milli over 10 milli area, and I will do the 5 tests on this. One is here, one is here, one is here, and one is here, one is here. Okay, I'll do the 5 tests on this surface. It's not wise. You need to allow sufficient amount of space from the edge of the specimen. From the edge, if you want to do the testing, from the edge the distance should be 2.5 to 5 times the diameter. Let's say 5 times the diameter of the ball. Okay, so you need to be really careful about that, because edge will have the effect. Okay, if you do the indentation test on the edge, then because of this free surface, the diameter will not be the exact that you get on the inside of the material, because there is not enough support of this material, because there will be deformation on the outer surface. Okay, so that will change the result. And finally, the uniformity of the material. Material should be uniform. If there are some places where the material is not uniform, for example, you have given a piece of steel which is joined by welding. Okay, and you have been told to do the hardness test of the base metal, not the welding zone. Okay, then you have to do the test on the base metal, not on the welding zone or the heat affected zone because of the welding. You cannot do the test here and say that this is the testing of the material. So material has to be uniform. This is just for an example. Okay, and it actually indicates the uniformity of the material where you do the testing. Okay, anyway, any question? The applications that I was talking, the Samira was talking about probably. The Renal hardness test is mostly used for castings part, steel, cast iron, aluminum. Rockwell hardness is for the finished parts, gears, valves, pulleys, cutting tool, sheet metal, plastic parts are also can be tested using the Rockwell hardness tester. Okay, and Rockwell superficial hardness tester is used for shallow penetration, very small penetration, thin case hardened part. The material is heat treated on the surface. Let's say you have a material here and the surface very small thickness was heat treated. Then you need to use the superficial tester so that the indentation does not penetrate through the top layer of the material. Okay, so that in that case we use the superficial hardness tester. A very small thickness can be part can be done, and Beakers hardness is for thin parts, mainly used for thin parts. And micro hardness test for plated surface coating, laminated material. If there's coating on a surface and you want to do the hardness test of a coating which is very thin, right? And to do the testing you can use vinyl hardness, and sometimes grain and grain boundary hardness. That what I said, like in the case of crystals, you can also do the hardness test on the crystal, okay, using the micro hardness tester. So these are the applications where you use different hardness tester for different applications, okay, for the purpose of comparison. Any question? Okay, so the next part of the destructive test is like tensile properties. Since you already know these properties, I'll just go through this very slowly, very quickly actually, to finish it up. Just to remind you about all these parameters, because you have already studied them in your solid mechanics class. For tensile properties, if you when you do the tensile test, you already know all these things. Just to remind you, the proportional limit. What is proportional limit? Up to which the stress and strain is linear. Stress increases with strain linearly. That is called proportional limit or elastic limit. You can also say the elastic limit. And yield strength or yield point, beyond the proportional limit, there is a point after which there is no change of uh, stress with the increase of strain. That is called yield. Okay, and that point is called, the point where it starts is called yield point. Okay, and the ultimate strength is where the maximum point, the highest point of the stress strain curve for a tensile stress strain plot. It's called ultimate strength. Fracture strength, where the fracture occurs, and the modulus of resilience is the area under this curve. Okay, this area is called modulus of resilience. Modulus of resilience can be represented by two ways. One is if you calculate this area using a stress versus strain curve, then you will get it like megapascal. Okay, because half into base into height. Okay, then strain does not have any unit, so stress will have megapascal, so it will be megapascal. And if you use like load versus displacement diagram, then you will get the since this is energy, actually modulus of resilience is energy, so in this case you will get like Newton meter. Okay, Newton meter or Newton millimeter. Newton meter is the joule. Okay, you'll get the energy as joule. And the modulus of toughness is the area under the curve up to the fracture. Okay, this whole area is called the modulus of toughness. That means how much energy a material can absorb up to the failure. Okay, up to the fracture up to the fracture point, the amount of energy that has been absorbed by the material. Okay, and the modulus of elasticity is the slope of this curve. Slope of the stress versus strain curve is called, this is the slope. So how do we measure the slope? If you know the proportional limit, then the modulus of elasticity E is equals to delta delta sigma, or that means delta sigma divided by delta epsilon. We measure the modulus of elasticity using this equation. Okay, this will be
Sir,
the
yield point
yield point is the point where after which, okay, the point after which there will be no appreciable change in stretch, okay, with the increase of strain. See, there is no appreciable change in stress with the increase of strain. That means it remains almost constant. Okay, the stress becomes constant, just strain increases, and the point at which this phenomena starts is called the yield point. That means after which material is permanently deformed. Okay, did you understand? Hello.
yes, sir.
Hmm.
Yes.
Okay, any other question? And the standard for metallic materials that is used for tensile property measurement is ASTM E8. Just for your reference, if you want in your next year, in the fourth year, you're going to do the final year project. If you want to do any kind of project with the metals, then you can use this standard ASTM E8 for metallic material. So for different material, there are a lot of enormous amount of standards nowadays available. It's kind of business, but anyway, we need to follow it to get our paper published. Okay, and for the brittle material, the first one was for the ductile material, and then this one is for the brittle material. For the brittle material, the proportional limit is same as the other one, and the yield strength or point is kind of different here. Okay, because for the brittle material, it suddenly fails. Actually, it goes up and then boom. Okay, it goes up like this and then boom. That means it fractures suddenly with very small amount of elongation or strain. So in that case, how do we get the yield strength? To get the yield strength, we use another term according to the standards. Actually, is the yield point at offset, certain offset. Okay. So we get the proportional limit, we get the modulus of elasticity, we get the modulus of resilience and toughness similar to the previous one. Uh, if this is the fracture point, then area under the curve is called the modulus of toughness. And if this is the elastic limit up to this point, this is the elastic limit, then this area will be the modulus of resilience, and fracture strength will be at the fracture point. Okay, and that will also be the ultimate strength. Okay, the fracture strength is also same as the ultimate strength. These two are the same for the brittle material. Okay, and to get the yield strength, you see this line. This line we say that this line we say the modulus line actually. Okay, the slope of this curve is same as the modulus of elasticity. And
Yes.
at 1.1% strain, we draw a parallel line, and that the point at which this parallel line intersects, we call it the yield stress or proof stress. Sometimes we call it proof stress too. Okay, and that is actually yield stress at 0.1% strain. Okay, did you understand this one, the yield point? Did you get it? Anybody?
Yes, sir.
Okay. If you understand, that's okay, but if you don't, then it will be really problem. Okay, because these are the basic things of a mechanical engineer need to know. So you should make it really clear. And sometimes for this is very easy way. Okay, this is the usual way it should be have. The material should be have. These are the usual ways. But sometimes in the case of ductile material, you'll find like a you'll not find any specific yield point. Can you see, is there any yield point? According to the definition of the yield point, the definition of the yield point is that there should not be any change of stress. It should be like this, and then we can say this one is yield point. But that's not happening in here. Then how do you get the yield point? In that case, you use this method. You use at 0.2%, you get a point, and at that point you say this is the yield point. Okay, so that's how there are other standards also available for measuring the yield point.
Okay, sir.
And this is the comparison. No, this is for the compressive properties. And for the compressive properties, this also same. Okay, the tension property and compressive property are almost similar way. The curves will be the same, and also the measurements and calculations or energy absorption, all other things will be the same. In the case only the necking will not occur. Instead of necking, what will happen is that it will be densification. Okay, and that stage is called beyond that ultimate strength, it is called the densification of the material. This is only the difference between the compressive properties and the tensile properties. A standard for material is again the STM-E8. Okay, the next one is Choppy impact test. Sorry, impact test. How do you do the impact testing? Okay. To do the impact testing, we have three different methods: Choppy impact test, Azide impact test, and drop weight impact test. and this one is not in your book. It's my edition anyway. So for Choppy impact test, how does it work? You raise, there is a setup like this with a hammer. It's kind of pendulum, okay? And that hammer, when you raise up to this point, it will have a potential energy of mgh. When you release it, it strikes on the specimen and then get raised again on the other side, which is H, where the potential energy will be mgh. So how much energy has been absorbed during breaking of this specimen can be calculated as kV equals to mg capital H minus mg small h. That means the impact energy is basically the amount of energy required to break a specimen. Okay. And what is the specimen and how the specimen is placed? If you are doing Izod impact test, Choppy impact test, if you are doing the Choppy impact test, the specimen will be like in the cantilever arrangement, and the hammer will strike on the back of the specimen, and you need to also provide a pre-crack on the surface so that the material can break from this point. Okay. Material can break from this point. And for the calculations for Choppy impact test, the specimen orientation is like this, and the size of the specimen is also constant, that is 10, 10, 75. Okay. And also there are some other parameters for the for this groove cutting. Okay, that is also available in your book, so you can also have a look at that. And for Izod, the arrangement is cantilever type. For Izod impact test, the principle of operation is same as this, but the orientation of the specimen is different. That is cantilever arrangement of the specimen, and the pendulum actually strikes in here, so that material can break through this point. And you need to calculate the change of energy, how much energy is changing, that means absorbed by the specimen, and that will give you the impact strength. And the final one is the drop weight impact test. In the case of drop weight impact test, you raise a weight, a certain amount of weight from the surface of the specimen, and you calculate the energy that has been stored on potential energy stored on this specimen. Once it strikes on the specimen, then using a load cell on here, you can calculate the how much force is absorbed by the specimen and how much energy is absorbed by the specimen. Okay, and that will give you the analysis results. For example, like force versus displacement, you'll get the graph of force versus displacement. Force will increase and then decrease. Okay, and then get flat, and then using this area under the curve, you can calculate the energy absorbed by the specimen. Okay. Okay, any question here?
Yes, sir.
Any question on Choppy, Izod, or drop weight impact? No. All right. Then what is the for example, what is the application of this drop weight impact test? Is that, for example, if your let's say you have a plastic door at home, okay, you a kid is throwing his toy on the door, okay, then how does the door behave? How much energy the door can sustain? Okay, for calculation of all these things, we actually use the drop weight impact test. Okay.
Yes, sir.
Okay, next is the fatigue. Fatigue is a very common phenomena. And no, there are only 2 left. I want to finish this lecture, otherwise there will be broken. Okay, it will not take long. I think within 5 minutes you can finish this. It's very small. Okay, for the fatigue test, we have 2 different parameters to be determined. One is fatigue strength and another is fatigue limit or endurance limit. In the machine design, you have already studied what is endurance limit. Okay, in the case of fatigue testing, we actually apply the cyclic stress, okay, cyclic loading. For example, you have a specimen here, you use the apply the force in the tension. That means you increase the tension force up to this 5 megapascal, and then you decrease it to the 0, and then you compress it. You do the apply the force in tension, and then you apply the force in compression, and this will complete a cycle. And similar way, another cycle. Okay, another cycle. Sorry, not here. The one cycle will be like a start point to the end point. This is the tension side, this is the compression side. Okay, you apply the cyclic loading, and then you will get a graph like this for fatigue strength. The SN curve is very important for to determine the fatigue limit of a material. For example, if your material has a yield strength of this much, then material will fail at the first cycle. Okay, if you apply the maximum load less than the yield strength, then you will get these points. The material will fail after certain amount of cycle. Material will fail if you lower the strength, then the material will fail later. Okay, it will survive for longer period of time. After some time, the material will not fail. Okay, it will operate unlimited number of cycle, and that is called the fatigue limit of that material. That means if you apply load in a material in such a way that the stress on that material is does not is less than this limit. Okay, for example, the material has a yield strength of 120 and the fatigue limit is 60. Okay, for your design, if you use that 60 megapascal in your design, then the material will provide service unlimited amount of time. But if this point is 80, if you design this based on 80 megapascal, design the part based on 80 megapascal, then material will fail after certain number of cycle of operation. After certain number of cycle, material will fail. Okay, and this curve actually shows you the what should be your how long the material will survive. So nowadays people actually design the material within these ranges so that they can say, like, for example, in the case of electronic component, after 3 years it becomes useless because they actually do not use the endurance limit for designing them, because you need to renew your specimen and they need to increase their cells. Okay, the next is also the fatigue, but in the case of what is the that's what we said, like that is the fatigue limit. But what is the fatigue strength? The fatigue strength is a strength of the material. In the case of some materials, you will not be able to find the fatigue limit. Okay, there are some materials which does not have the fatigue limit. In that case, the material B is showing such behavior. It does not have any fatigue limit. Then you need to choose a strength and the number of cycle. Okay, in that case you can say, like, the fatigue strength of material B is this with n1 number of cycles, n number of cycles. For example, fatigue strength is 60 megapascal, and it can survive 10 to the power 7 cycles. That's how we specify the fatigue strength. Okay. So, okay, any question? I think you guys are
ফ্যাটিক লিমিটটা আমরা কিভাবে বের করি স্যার?
Okay, what was that? Fatigue limit.
ফ্যাটিক লিমিট
How do we determine fatigue limit?
কিভাবে বের করি এটা?
Okay, so as I said
sir.
in the first slide, in here you are applying the stress on the material, right? You are increasing the
sir.
strength from 0 to a certain limit. Okay, let's say a material has a yield strength of 60 megapascal. You are applying force, the 60 stress 60 megapascal. In here 60 megapascal you are applying. So the material will fail at this point, right, within one cycle. But if the maximum stress is, you reduce the maximum stress to 50, then it might operate like 10 cycles. Okay, if you reduce the strength further, like make it 10, it might serve you like 10 to the power 5 cycles. And if you use 5 megapascal load, it will give you unlimited amount of cycles. So the 5 will be the fatigue limit. That's what is shown in this image. Okay, if 120 is your yield strength, if you apply the stress 120, then material will fail immediately in one cycle. If you use 80 megapascal, the material will give you certain number of cycle, and after this at a load of 60 megapascal, the material will give you unlimited amount of cycles. Then you need to do all these tests. You need to do the test 120 at 120 megapascal, you need to do the test at 80 megapascal, you need to do the test uh, some more points, and then finally you will get here like at 60 megapascal, you get like unlimited amount of time material is not failing. So 60 will be the fatigue limit of that material. Did you understand?
Yes, sir.
Okay. So the next one is the creep test. Creep test is carried out at high temperature. Not necessary that always it will be at high temperature. Below yield strength, and temperature and applied load remains constant. You have a specimen with a gauge length of L naught. Okay, and you are applying a force, constant force, let's say F amount of constant force on the specimen, and after 1 hour, let's say the temperature, you have also increased the temperature is like 200 degrees Celsius. Okay, and after 1 hour you'll see that the material has elongated. Initially you will not be able to see there will be no elongation. Okay, but after some time there will be elongation, and that behavior is called the creep of the material. Okay, and how does it occur, and how does creep occur? Okay, and to show that, this is the elastic strain. Okay, after the application of load, immediately there will be a deformation. Okay, initial deformation. Okay, after that initial deformation, you measure the length here that I was showing here. After the application of this load, you measure the gauge length, and after certain time, 1 hour, 2 hour, 3 hour, 4 hour, you measure the gauge length. Okay, this gauge length will change with the time. Okay, the gauge length changes with the time, so because of the creep. Okay, this is the elastic strain. The material actually starts in here. With the increase of time, the percent elongation is increases. Okay, and that increase is increases very rapidly. Okay, in the primary creep zone. Okay, initially it increases very rapidly, and in some cases it increases very rapidly and then stop increasing. With the time, the material does not that means material does not elongate, and this is called the creep limit of the material. Okay, this is called the creep strength of the material. That means at that kind of load and the temperature, the material maximum elongation on the material will be this, and this is the creep of that material. Okay, and this is better. Okay, this material will not fail. But in some other cases, it is seen that the second stage of creep comes into play, and in the second stage of creep, it is very steady increase of the dimension of the material, very steady elongation of the material occurs in the secondary stage of creep. This one is also okay, because there will be huge amount of time from this point to that point. Okay, huge amount of time the material can survive. Okay, and there will be no change, no failure. And when the material goes to the tertiary creep, that is the alarming point, because it can fail anytime in the tertiary stage of the creep. That is why if you want to design a material, it has to be between either in the primary creep zone or secondary creep zone, or it has a creep strength. Okay, that means it has maximum creep strength. That means within that temperature and that load, the material does not fail at all. Okay, and or it moves to the secondary stage of the creep with a very long time. Okay, the very long time, then you can say that the material will be safe in terms of creep. Okay, any question? No, I think you guys are really tired. It's 11 o'clock anyway. So in the next class, we will be discussing the non-destructive tests. Okay.